Hello and welcome to the Museum of Atoms. Feel free to handle any of the exhibits. Our friendly expert guides are on hand and we'll be very happy to let you know where the atoms are or how fast they're travelling.
I'm Stuart Kenny. I'm a PhD student in the Department of Electronic Engineering at the University of York, and I'm currently working to build an atomic clock. And as will be immediately apparent, this is my first time recording a proper video.
And I'm Helen Smith, Professor of Renaissance Literature in the Department of English and Related Literature at York, working on a book about matter and its shapes in the 16th and 17th centuries. So, atoms were invented around the turn of the 5th and 4th centuries BC by Lucretius, a pre-Socratic philosopher about whom little is known.
Wait a minute, atoms weren't invented.
They've existed for at least 13.8 billion years. Then it took a while for us to turn up, and longer still to figure out how the building blocks might work. Theories on the beginning of the universe suggest an event of extraordinary power. Then, as the universe cooled, neutrons and protons could bind together to form certain atoms. As the physicist and astronomer Chanda Prescott Weinstein sums it up, we're pretty sure that during the first sliver of a trillionth of a second, the universe expanded very rapidly, so that for the most part it looked the same in every direction and looked the same from every position. Except that particles started to blip out of nothing due to random fluctuations caused by quantum events. Maybe in space-time, we're still not super sure about that. Then again, we're not super sure about this either. For some reason, those particles formed more matter than antimatter. From there, those baryons started to form structures, and from those structures, stars formed. Then the stars got old, and some of them died in super epic, rather fabulous fashion. They exploded into supernovae, making heavy elements like carbon and oxygen in the process. Those elements went on to be the basis for all life on Earth.
Okay, created, but invented too. An atom is also a way of thinking. Since at least the time of Lucretius and his better-remembered pupil Democritus, people have been fascinated by the idea of something almost indescribably small, virtually imperceptible, but fundamental to existence. I'm interested in the hold atoms have on our imagination, how philosophers, writers and others have used the idea of atoms to extraordinary creative ends.
Perhaps we should offer a disclaimer here. This is not, except tangentially, a talk about the development of physics and the understanding of atoms over roughly the past 2 centuries. There's no Cavendish laboratory here, no Marie Curie, no Rutherford, no Niels Bohr Institute. There's no uncertainty principle and no cats in boxes.
Oh, fine.
So, back to the invention of atoms. Much of what we know about the ideas of Democritus and his mentor Lucretius come from the works of Aristotle, in which he summarises earlier ideas about the substance of the cosmos, mainly in order to be rude about them. Democritus and Lucretius, he reports, say that there are indivisible bodies, infinite both in number and in the varieties of their shapes, of which everything else is composed. These are atoms, atomos, meaning literally uncuttable, but also, and charmingly, the twinkling of an eye. They are, for Democritus, impassive and unchangeable. Scornful as he is about every other philosopher, Aristotle acknowledges that the most systematic and consistent theory of the material universe, and one that applied to all bodies, was advanced by Lucretius and Democritus. Lucretius, Aristotle says, argued that there could be no motion without a void. Atoms must exist in a universe full of nothingness. It is when atoms come together in the void that things, people, animals, planets, stars come into being. A whirling motion sets a cosmic whirlpool in action, drawing together atoms until they form so large a mass that a cosmos, a universe, fragile and impermanent, is born. For Democritus, who synthesised Lucretius' theories, and whose own philosophy is much more widely attested, though his own writings don't survive, everything was made of atoms. When you see something or smell it, a thin skin of atoms is hitting your eye or wafting in at your nose. Properties like colours or taste are, for Democritus, a convention, something we have agreed to trust in, whereas atoms and the void are truly real. And thought, as much as perception or sensation, is material for Democritus, a product of the arrangement and rearrangement of minuscule bodies. It's important to remember that other atomic theories and systems existed at the same time, and almost certainly informed the thought of Leucippus and especially of Democritus, who, according to the gossipy 3rd century biographer of the eminent philosophers Diogenes Laertius, spent the whole of his family fortune travelling to Egypt to study geometry, to Persia and the Red Sea, and to India and Ethiopia, all in pursuit of natural philosophical knowledge.
Why should you never trust an atom? Oh, order of continuity. Why should you never trust an atom?
Because they make up everything. Now let's jump forward 3 centuries. Enter Lucretius, the great poet and philosopher of atoms, whose De Rerum Natura, On the Nature of Things, is an extraordinary lyrical 6-book poem that remains the greatest, most comprehensive account of Epicurean philosophy. The first 2 books of De Rerum Natura are concerned primarily with atoms, their shapes, properties and movements, the laws that govern their combination and taking form, and, of course, this being ancient philosophy, perhaps simply this being scholarship, a little bit of time being rude about everybody else. Still worse, he says about Heraclitus, he makes his atoms flimsy. Lucretius's poem is nothing if not ambitious. I open for you by discussing the ultimate law of the gods and sky. I reveal the atoms whence nature creates and feeds and grows all things, and into which she resolves them when they are spent. Lucretius mocks the philosophical premise of creation ex nihilo, or from nothing. Remember here King Lear's conviction that nothing will come of nothing, too often interpreted as a message about finance and investment, rather than a sweeping intervention into debates around the formation of the world. Lucretius also has a lovely sense of the particularity of atoms, the requirement that the conditions should be right for their combination to be fruitful and for fertile life to endure. Since all creatures rise from their own seeds, they need a place stocked with their stuff, their atoms, whence they are born and emerge to the shores of light. Everything can't just spring from anything. Inner capacities make things what they are. Why too does the rose bloom in spring, grain ripen in summer, unless the seeds specific to each thing join at the right time to reveal the creature which the mild weather and quickening earth will bear safely, so tender it is, to the shores of light. Above all, Lucretius insists, atoms persist, even when everything crumbles. Nothing returns to nothing. When things shatter, they all return to their constituent atoms. There's a wonderful doubleness in that first line. At first reading, it might feel despairing. Nothing comes from and returns to nothingness. But that's not what Lucretius means. It is not possible, he says, for anything to simply disappear. Instead, its atoms continue and become part of the cosmos again. Now, Lucretius is pretty clear that atoms are indivisible, that they can't be split, though he does also say that they're made up of 3 tightly packed points or vertices. There is something inside the atom for Lucretius, as for Epicurus before him. Lucretius asks us to remember that there's no bottom to the universe where the atoms might stand tight, since the limitless span of space stretches unmeasured forever in all directions. Instead, atoms move constantly through space. Intriguingly, the movement of atoms is something that Lucretius suggests we can deduce from the motion of tiny motes of dust, what he calls sunlight flecks. These, he argues, are the moment when atoms become visible. One atom bumps another and joins together, they bump into more, forming eventually a cluster just big enough to be seen by the human eye in the right light and the right conditions. And from this, Lucretius argues, we can work out the essential motility of atoms. But hurried by tireless motion, this way, that way, some crash head-on and rebound over vast chasms, while some veer slightly apart from a close-dealt blow, and atoms that jar and rebound over tiny space so tightly wedged in their assembly, tangled up in their snagged shapes, intertwined and locked, these constitute the strong rock roots, the rugged structure of iron, and all things of like strength. I love how these lines seem to want to imitate what they describe. Telling us that tangled atoms form the most dense and weighty objects, his language folds over on itself, twining and locking like the tightly packed atoms of dense substances. But the rest, the few that wander the great void, ricochet far and round from afar vast chasms in speedy return. These atoms furnish for us the thin air and the sunlight in all splendour. Though this passage might suggest a whirling or chaotic motion, for Lucretius, the collisions of atoms are famously caused by a chance swerve. Atoms stream through the void in a straight line and, at an utterly random time and a random point in space, they swerve a little. Quantum physics, eat your heart out. Lucretius is relentlessly materialist. He too is insistent that atoms are of different shapes and sizes. Olive oil flows more slowly than wine, he says, because its atoms are bigger or more interhooked up with themselves and twined. Listen again to how his language hooks and tangles in imitation of those intertwined atoms. It's the shape and connection of atoms that affects how we sense any object. And to illustrate that point, Lucretius asks us to reflect on our own experience of taste. Here notice that a sip of milk or honey rolled on the tongue will lend a pleasant feeling, while sickening wormwood and harsh centauri pucker the mouth with the twists of their foul taste, and your mouth puckers there as you read those lines. Easy for you to see that smooth and rolling atoms compose what touches the sense with pleasure, while what seems harsh, bitter, these things are stitched and held together in more hooked connections, which forces them to wedge and split their way into our sense, slashing through the body. Smooth atoms create smooth sensations. Sharp atoms make us wince. There's a lovely passage just following this one in which Lucretius argues that the serrated teeth of a saw palpably can't be made of the same atoms as the rolling, smooth sounds of beautiful music. All of these things, these sensations, are, for Lucretius, the physical effects of atoms acting on our bodies. This is part of his division of all things into properties and accidents. Those things that really exist possess a physical reality, and those which are social or conventional. This is one of the points at which Lucretius's Epicureanism is evident. Thinking about atoms is, for him, a moral as well as a scientific endeavour, and one that should teach us to reject the ephemeral trappings of the world. So where we've seen Democritus think about properties as the reality of atoms and colours and tastes as conventional, Lucretius's division is conspicuously between the tangible reality of things and the petty concerns of human politics. Pick anything you like. Of matter and space, it's either a property or an accident. The first is so conjoint it can never be divided from things without destroying them. Rocks must be heavy, fire hot, water fluid, all bodies touchable while the void remains untouched. But slavery, riches, poverty, war and peace, freedom and other such, whose chance arrival or chance departure leaves the nature of things intact, these we call, justly, accidents. These things, in other words, are neither natural nor enduring, and, by implication, they can be changed, though that may not be quite the lesson that Lucretius wanted us to take away. Now, prior to Lucretius, some thinkers held that atoms weren't just phenomena to do with matter, but that we could think too about atoms of geometrical extension, the smallest portion into which you could cut a line, in other words, and even of time. But Lucretius is firm. Time is not material. Even time is accidental. From things themselves, our sense derives its notion of past action, of what is happening now and what will follow. Time is simply something we extrapolate from our experience of the physical reality, the palpable stuff of the world.
Fortunately, I'm only dealing with Newtonian time. Time is continuous, absolute, linear and divisible, and I'm not working at accuracy levels that require me to delve into Einstein's general relativity.
But what do you mean by an atomic clock? Isn't every clock made of atoms?
The concept of using atoms to keep time perhaps began with James Clerk Maxwell in the 1870s. In 1879, William Thomson, who would later become known as Lord Kelvin, published a statement that he attributed to Maxwell, that atoms could serve as natural standards of time and length. They recognised that atomic transitions could be a very reliable way to perform accurate scientific measurements. If atoms truly are alike, then each atom will behave identically in response to the same stimulus. In the 1930s and 1940s, Isidor Isaac Rabi and his colleagues at Columbia University took the next big step. They proposed that magnetic resonance could be used as the basis for an atomic clock. Rabi demonstrated molecular beam resonance in 1938. He showed that lithium chloride molecules could have their nuclear spins controlled by a small oscillating magnetic field, and this could be used to alter the trajectory of a stream of these molecules. Think of a beam as being the path taken by an individual lithium chloride molecule as it travels from one end of a tube to the other. Now, have more molecules follow this exact same path, but one at a time. Rabi's experiment passed this beam of molecules through a strong, uniform magnetic field. The beam also passed through coils of wire in the form of a hairpin, which were used to create a small radio frequency magnetic field at right angles to the first. Rabi showed that if the radio frequency was close to the Larmor frequency... Hang on. Remember physics classes years ago? Electric currents cause magnetic fields, and current is charged particles moving? Good. Well, an external magnetic field can cause a positively charged proton to wobble or orbit in that field. If the frequency of the field is just right, it sets up a stable orbit for the proton within the atom. And if you're a physicist, you might say that the atom is precessing at its intrinsic Larmor frequency. So Rabi showed that if the radio frequency he created was very close to the Larmor frequency, the beam of atoms could be deflected. Even though these molecules are only weakly magnetic, a 245 centimetre long beam was enough to make the deflection detectable. The first atomic clock arrived in 1949. It was developed by Harold Lyons at the US National Bureau of Standards, and it was based on an ammonia absorption line at 23.87 gigahertz. You can see the inventor on the right side of this picture, along with the ammonia clock. Look closely and you'll be able to see the absorption cell wrapped around the clock face. Ammonia was stored in this 30-foot long tube. Microwaves were injected at one end and detected at the other. If the frequency was right, it would be seen as a drop in power received, as the energy was absorbed by the ammonia. Lyon's clock never surpassed the stability of quartz oscillators, but it was a powerful demonstration that the principle was sound. It was Louis Heston at the National Physical Laboratory who produced the first cesium beam standard in 1955. That's Heston on the right of this picture. Building on very disruptive work at the NBS, he used the hyperfine properties of a beam of cesium atoms to make the world's most accurate lab-based clock. Physicists have some wonderful terms. The gross structure of an atom is a list of all possible energy levels, ignoring electron spin. The fine structure adds more detail to the energy diagram, and it includes the magnetic moments of electron spin, the turning forces associated with each electron. Even smaller in magnitude are the hyperfine energy levels, small shifts in energy due to magnetic interactions between the electrons and the atom's nucleus. This is what Heston uses. A stream of cesium-133 atoms, each having a single electron in its outer shell, which can be excited from a ground hyperfine state. That's the lowest possible energy state into an active or higher energy state by the correct application of a microwave field. His equipment is very similar to Rabi's beam apparatus, though it has been upgraded to use a technique called Ramsey interferometry. So now, the atoms pass through two microwave magnetic fields, reaching a detector at the far end only if the atoms remain in their excited state. This technique and choice of physical phenomenon allow Heston to claim an accuracy of 1 part in 10 to the 9. That's 1 second every 32 years, with greater potential when improvements in his electronics allowed.
Okay, wait a second. However you want to define one. How does any of this give you a clock?
It doesn't. I'm being an engineer here and considering anything that beats to be a clock. I want to generate an electrical signal that beats. In other words, build an oscillator, and I want to feed that into something like Heston's cesium beam apparatus to check that I'm generating the correct frequency, which I can confirm by seeing a physical deflection or an absorption. If the frequency drifts, I can tweak the oscillator to ensure the correct physical response. This is using the physics package to discipline an oscillator, and it vastly improves the long-term stability. Heston's atomic clock and the ammonia cell wrapped prominently around the clock face show that anyone wanting to tell the time can. You need to divide the oscillator output by its frequency, and this produces one tick every second, and count seconds in the conventional manner. Heston's breakthrough marked the first time that a lab-based clock could provide better accuracy than astronomical observation. Subsequent work with the US National Observatory eventually led to the second, that moment of time that we take for granted, being defined as 9,192,631,770 transitional cycles of cesium-133. That's the definition that we still use today. Before it was possible to use the properties of atoms, we relied on the physical properties of objects. The accuracy of a quartz oscillator is mainly limited by how well a pure crystal can be machined into a small monolith. In 1923, state-of-the-art quartz oscillators had an accuracy of 1 part in 10 to the 5, or 1 second per day. In other words, that's how much time they could lose or gain in a day. Pendulum clocks were invented in 1656, and by the 1920s, these could operate with an accuracy of 10 milliseconds per day, though they required regular calibration. These complicated systems depend on how accurately cogs, springs, and pendulums can be engineered to make their interactions as precise as possible. Cesium beam tubes are accurate to 1 part in 10 to the 14, or 1 second every 3 million years. The best optical lattice clock today has a relative precision of 2.5 times 10 to the minus 19, meaning that if it had been running since the start of the universe, it would have neither lost nor gained more than 100 milliseconds.
Why should you never go to dinner with a francium atom?
Because it'll split on you before the bill.
So it's splitting before the bill arrives. Try again. Why should you never go to dinner with a francium atom?
Because it'll split on you before the bill arrives.
Since 1900, theories about the structure of the atom have evolved rapidly, from J.J. Thomson's plum pudding proposal in 1904, which was rapidly displaced by his own student, Ernest Rutherford's 1911 model, which situated the nucleus at the centre like a gnat in the Albert Hall. The 1913 Bohr model is a modification that adds orbital electron shells, and Erwin Schrödinger's equation, published in 1926, explains electron behaviour as wave functions, which is mathematically neat, but a devil to visualise. The resulting atomic orbital model, with electron positions being represented by probability functions, remains today's benchmark.
Speaking of plum puddings, it's easy to imagine that molecular gastronomy, the study of cookery at a level that exploits the properties of molecules, atoms, and chemical reactions, is a modern invention. The term molecular and physical gastronomy was, after all, coined in 1988 by the Hungarian physicist Nicholas Curti and the French physical chemist Hervé Thys, who cooked up between them a series of workshops bringing together professional chefs and scientists. In a story as old as science, the roots of this idea can be traced to a seldom acknowledged woman, in this case Elizabeth Cawdry Thomas, who ran a cooking school and associated closely with many physicists. Her interest in the science of cooking was one of the provocations that set Curti and Thys's workshops in motion. But I want to reach earlier than Cawdry, to Sir Kenelm Digby, pirate, courtier, philosopher, and, supposedly, inventor of the glass wine bottle. 4 years after Digby's death in 1665, a curious book was published. The Closet of the Eminently Learned Sir Kenelm Digby Knight promised its readers recipes for making of metheglin, spiced mead, cider, cherry wine, etc., together with excellent directions for cookery. Notably, in a recipe for metheglin called the liquor of life, he asks the maker to pour liquid into yeast every time from high and working it well together, that so every atom of the yeast may be mingled with every atom of the liquor. In a second recipe for metheglin, Digby again insists on pouring the cooled liquid from a height to make sure it will break and dissipate the balm into atoms. If they want to, the recipe user can also atomize the resulting concoction with ambergris or musk and spray it around a room. Don't forget that perfume atomizers are still with us today. An earlier recipe collection, The Ladies' Cabinet Enlarged and Opened from 1654, similarly instructs readers to automatise a rosewater syrup. And moving into the realm of medicine, in 1673, the cook and teacher Hannah Woolley informed her readers that illness might be carried in the air, adding as proof, "I have heard it reported by an eminent physician that let any person newly come out of the bath go into a place where quantity of dust is raised, and he shall instantly feel an universal pricking over his whole body, which is nothing else but the atoms of dust drawn in by the arteries." These curious recipes and medical observations do two things. First, they illustrate the very fine line between domestic practice and natural philosophical experiment throughout the 16th and 17th centuries. Natural philosophers were fascinated by what went on in the kitchen as well as in artisans' and artists' workshops. Let's not forget that foundational chemical and physical observations were rooted in watching and learning from women's intimate practical engagement with the properties of ingredients. Second, they give us a sense of how exciting the idea of atoms was in this period across many walks of life, and of attempts at practical application, not just thinking about atoms as a philosophical problem, but attempting to observe them, interact with them, and, going further, to exploit what they could do. The 17th century was a period of tremendous developments in the science of atoms, though these tend to get written out of the textbooks because they're seen to be philosophical rather than empirical advances. But this was a century of Pierre Gassendi and Robert Boyle, of natural minima and corpuscularianism, and, of course, of Isaac Newton. Digby doesn't often make it into this rarefied pantheon, but he was an enthusiastic atomist. He argues that light, that subtle and rarefied fire, necessarily carries away a few atoms from all the bodies it meets, just as a ball would carry with it some of the moisture of the wall against which she is banded if the plaster thereof were also moist. Digby insists that small quantities of atoms can be transferred from one object to another and can break from a body, leaving an invisible trail. How else, he speculates, do dogs follow a scent? They find in a great heap of stones that which a man hath touched with his hand. Therefore it must needs be that upon the earth or upon the stone some material parts of the touched body remain. The person who is being hunted has left a little pile of atoms sitting on the stone, ready for the dog's keen noses. Concluding that the air is full of atoms, Digby asks why bodies which lose atoms don't diminish. His answer is twofold. On the one hand, they do, he says. Just look at substances like the spirit of wine or musk, which evaporate. On the other hand, he argues, each atom may be divided, stretched and carried to a marvellous distance. His analogy, or his example, is gold, beaten to an impossible thinness. One small button of gold may be so extended that it may reach from this city of Montpellier to Paris and far beyond it. Into how many millions of atoms might not this gilded line be cut with small scissors? I love this image because it seems to me that though it's tempting to say, well, they're not really talking about atoms, just about very small pieces of things, here we see a 17th century thinker really trying to wrap his mind around the kinds of scale that allow us to conceptualise the startling tininess of atoms in ways that popular science accounts and textbooks routinely do today. We've already seen that Digby was interested in cooking with atoms. He was also interested in how understanding atoms might transform medicine. Digby is famous for his weapon salve, a medicine which might be applied to the blade of the sword that cut someone rather than the wound itself, and which would prompt a stream of atoms between blade and cut, healing the patient even at a great distance. A caveat here, I wouldn't suggest trying this at home. In a different example, which suggests the influence of the Italian friar, philosopher and theologian Tommaso Campanella, Digby notes, "'Tis an ordinary thing. When one finds himself burnt as in the hand, he holds it a good while as near the fire as he can, and by this means the ignited atoms of the fire and of the hand mingling together and drawing one another, and the stronger of the two, which are those of the fire, having the mastery, the hand finds itself much eased of the inflammation which it suffered." Digby is really interested in ideas of attraction, how atoms might draw other atoms to themselves and might hook together, terms that are still of real interest to contemporary physicists, even if they would neither understand them in Digby's terms nor recommend holding your hand close to a fire in order to cure a burn. One final example, Digby follows this with what he calls an ordinary remedy, though a nasty one, that they who have ill breaths hold their mouths open at the mouth of a privy as long as they can, and by the reiteration of this remedy they find themselves cured at last, the greater stink of the privy drawing unto it and carrying away the less, which is that of the mouth. While I definitely wouldn't recommend this as a practical cure for halitosis, it is interesting to see Digby's attraction not just to the idea of atoms as indivisibly small and almost uncountable things, but to the questions of how atoms can be used. I can't resist adding my favourite moment from Digby, who asks us to imagine atoms like tiny riders mounted on flying horses. These atoms, he concludes, are like cavaliers mounted on winged coursers who go very far until that the sun setting takes from them their Pegasus and leaves them unmounted, and then they precipitate themselves in crowds to the earth whence they sprung, which though it be so thin that we cannot see it, yet we feel it as so many small hammers which strike upon our heads and bodies. Think of that next time you're out for an evening stroll. Think of the reality that you are being bombarded by countless invisible atoms. Think too about the flights of fancy which allow the willing scientist to conceptualise and try to make sense of that which can't be seen.
So, with the best atomic clock in the world currently maintaining an accuracy of 1 second every 8 billion years, and the smallest one sitting comfortably on a wrist, what is it that I'm trying to do with my PhD? I'm working on a rubidium vapour cell atomic clock based on a principle called pulsed optical pumping, or POP. Professor Jeremy Everard's group at York has developed a number of extremely low noise oscillators, and I aim to marry these qualities with the long-term stability of an atomic clock. Although the research community has made huge strides in improving the accuracy of physically large clocks, and wrist-sized clocks have been commercially available since 2011, I'm pursuing the middle ground. My aim is to try some new techniques that allow for a better quality, medium-sized, portable atomic clock to be available to communication engineers, to researchers in labs, radio scientists, astronomers, and applications that can't use GPS-disciplined clocks. As MPL's Dennis Sutcliffe neatly states in a 2014 interview, people always want things more accurate. If you improve the accuracy, then it may not be apparent immediately, but someone will come up with a use for it.
Just as we were finishing up this talk, a couple of exciting subatomic headlines hit the papers. A collaborative team of physicists at CERN have seen a charm meson, one kind of subatomic particle, oscillate between its states of particle and antiparticle. But, most pertinently to us, physicists have also embraced the challenge of making a massively more accurate clock. Not an atomic clock, but a nuclear clock. Does that mean that your whole PhD is pointless?
I've heard about this, and no, not at all. Though it will be really interesting to see if the team manage this. The team are trying to make the nucleus of a thorium isotope jump between two energy levels, and they're using an ultraviolet laser right at the edge of current engineering capability to do so. If they manage, it'll be great because they might make a clock that's 10 times as accurate as anything available today, and it'll also be largely immune to any stray electric or magnetic fields too.
A proton and a neutron are walking down the street, and the proton says, "Oh, stop, I've dropped an electron." The neutron said, "Are you sure?" And the proton said, "I'm positive."
As we said at the beginning of this talk, one of the things I'm fascinated by is the allure of the improbably small. I've already mentioned Shakespeare when I referred to King Lear, a play in which the distraught king on the heath threatens to crack nature's moulds, all Germans spill at once, to break the bounds of form and scatter the generative seeds of things. Now, I'm not here to suggest that Shakespeare has an extensively developed atomic theory. Quite the opposite, in fact. I want to point out just a handful of moments in Shakespeare which suggest his embrace of the comic potential of the atomically tiny, as well as his fascination with the limits of perception. Comedy first. In As You Like It, Celia, overwhelmed with Rosalind's barrage of questions, complains it is as easy to count atomies as to resolve the propositions of a lover. It's as much a challenge to answer the welter of questions coming from the anxious lover as it is to count atoms. And later in the same play, Phoebe, accused of having eyes that can murder the besotted Silvius, complains, "'Tis pretty sure, and very probable, that eyes that are the frailest and softest things who shut their coward gates on atomies should be called tyrants, butchers, murderers." Atomies A variant lexical form of atoms fairly obviously here just means something extremely small, though this idea of eyes closing themselves against a barrage of atoms takes us back to ancient philosophy and the idea that a skin or film of images enters the eye to let us see external objects. My aim isn't to claim that this is some kind of deep-rooted or overarching atomic theory, but to suggest the delighted imaginative play that Shakespeare finds in the idea of infinite, uncountable, tiny parts. Perhaps the quintessence, another scientific term of course, and one beloved by Shakespeare, of this kind of imaginative play with atoms comes in Mercutio's description of Queen Mab, who comes in shape no bigger than an agate stone and the forefinger of an alderman, drawn with a team of little atomies athwart men's noses as they lie asleep, her waggon spokes made of long spiders' legs, the cover of the wings of grasshoppers, the traces of the smallest spider's web, the colours of the moonshine's watery beams, her whip of cricket's bone, the lash of film, her waggoner a small grey-coated gnat, and in this state she gallops night by night through lovers' brains, and then they dream of love. This is fantasy at its delightful extreme, but it seems to me that Shakespeare is fascinated by the idea of things so tiny they flicker at the edge of perception like the fineness, the filminess of an insect's wings. There's a gorgeous passage in Love's Labour's Lust, where the grumpily misogynistic Boyer describes women's words as painfully sharp. The tongues of mocking wenches are as keen as is the razor's edge invisible, cutting a smaller hair than may be seen above the sense of sense. What I'm interested in here is Shakespeare's fascination with the point or the line at which the razor's edge disappears into invisibility, sharpened to such a degree that its cutting edge extends beyond that which can be seen, is reminiscent in some strange way of the tools that physicists need to use to measure or to manipulate atoms, themselves tools which extend beyond the capacity of human perception. So this extraordinary instrument, a woman's tongue, is able to split hairs with an astonishing degree of precision. The joke is that women can split hairs so small they're imperceptible. But at the same time, it seems to me, Shakespeare is keen to push his audience to do the imaginative work of conceiving of something so tiny, so fine, it escapes the senses. The atomic realm is the domain of the bafflingly small. It works as a way of extending the wit and imagination beyond that which can be seen and comprehended in the world. In the Mab speech, then, atoms are brought vividly to life, both in the sense that they are made a subject of creative play and in the sense that they're seen as inherently lively, a team of impossibly tiny horses riding roughshod through sleepers' brains. It seems to me, too, that this teases at the Democritean idea of thoughts, indeed of dreams, as wholly material, products of the whirl and clash of atoms. Shakespeare suggests that atoms pelting through the brain will change the shape of dreams. He does so in terms that have come to emblematise some of the most extraordinary imaginative feats of which the human mind is capable.
Why are atomic clocks so funny? Perfect timing.
An atomic clock relies on the behaviour of atoms in the absence of external stimulus. And in developing and constructing atomic clocks, and in pushing the boundaries of understanding to do so, it's become apparent that they need isolating from any external temperature changes. They need shielding from the Earth's magnetic fields, and at the highest levels of accuracy, they need to be kept absolutely still. An optical lattice clock can resolve the gravity time dilation associated with a 2 centimetre change in height. But on the other hand, some of these difficulties have also been usefully harnessed. The Zeeman effect can be seen when an atom is exposed to a small static magnetic field. And it's observed as a series of modified energy levels corresponding to the distortion in electron orbitals. Each level means a small shift in the hyperfine frequency, and whilst this is undesirable in an atomic clock, it's the perfect basis for a very sensitive magnetometer. The 1970s and the 1980s also saw significant development in nuclear magnetic resonance, that's NMR gyroscopes, hot on the heels of vapor cell atomic clocks. The unwanted rotation of a clock's vapour cell shows up as a phase shift in the precession of atom spins. Again, it's undesirable in a clock, but it's wonderfully useful as the basis to measure rotation.
Across the centuries I study, from the classical to the early modern period, philosophers and writers have thought about what language has to do with atoms. In different ways, contemporary physicists too struggle with the problem of describing something that can only be detected or observed through its actions rather than as an object. So what I want to suggest is that all the writers I have been talking about have been doing their best to see the atom, not with the extraordinarily fine, though also sometimes extraordinarily large, tools of contemporary physics, but with the resources available to them, poetry and the page. When, in On Generation and Corruption, Aristotle tries to describe what it means to imagine all things as being made up of astoundingly small parts, he reflects, owing to the changes of the compound, the same thing seems different and conflicting to different people. It is transposed by a small additional ingredient and appears utterly other by the transposition of a single constituent. For tragedy and comedy are both composed of the same letters. This is a question that's still of concern to modern physics. How do we make sense of the differences between things if they're all made of the same stuff? Aristotle doesn't mean that tragedy and comedy are spelled the same. That would be fairly self-evidently wrong. Instead, he means that a tragic play and a comic one use the same alphabet, but that the different combinations of those 24 different constituents, the letters, can make extraordinarily different things. Believe them, says Lucretius, picking up on this idea. As all words share one alphabet, so too many things may be made from the same atoms. And why? Notice that scattered throughout these very verses are many letters common to many words. Think about what it means to read these lines, to be directed into the book that you're reading as a way of thinking about the subject of the book, the impossible dance, movements and recombinations of tiny, indistinguishable things. But still, you must admit these words and verses diverge from each other in meaning and in sound. So many things the alphabet creates from a simple shuffle of order. But atoms allow more shufflings, therefore more variety. Poetry is a version of the dance of the atoms in the void, the alphabet a way of conceiving what it means to imagine the remarkable combinations and recombinations of atoms. And Lucretius is wonderful, I think, in his idea of language as a tool of scientific inquiry, a way of seeing deeper into the reality of the world. It does not slip my mind, he says, that the Greeks' dark findings are hard to illustrate in Latin verse. Above all, when our language lacks the words and new terms must be found to treat new subjects. And yet your virtue and the hoped-for pleasure of a delightful friendship urge me to persevere in my work, to watch through the calm night seeking choice words, the song by which at last I can open to your mind such dazzling light that you may see deep into hidden things. I love the pressure here that the combined mysteries of the universe and the challenge of translation place on language. How does the poet craft new words that can express the language of another culture and can take the right shapes to bring into being previously unknown truths about the universe? And I love the idea of watching through the calm nights, a process of meditative study where watching and hypothesizing about the stars and the universe is also a process of poetic inspiration and composition.
In the 1970s, physicist John Wheeler posed a question. May the universe in some strange sense be brought into being by the participation of those who participate? Participation is the incontrovertible new concept given by quantum mechanics. It strikes down the term observer of classical theory, the man, and the woman who stands safely behind the thick glass wall and watches what goes on without taking part. Maybe the writers you're talking about were participants all along. Perhaps they've still got one or two tricks up their sleeves.
And maybe an atomic clock is another way of describing the world, and a very beautiful one at that. But we are out of time, so thank you for joining us and for participating.